Are there any questions?
Yes.
Okay, let's see, today is Monday. Wednesday, we have a big deal lecture at 7. It's a public lecture that's probably worth going to because the speaker won the Nobel Prize in Physics for work on the cosmic microwave background radiation. So he's talking at 7 in Keller Hall. And actually there's a reception before that, but I was thinking we just end at sort of 7:15 sharp and then run over there. And catch the lecture. He's also giving the physics colloquium this week, but instead of being on Friday at 4, it's on Thursday at 4. And it's in the Math Science Study Center that's sort of halfway between Dane Smith and the library, right?
Yeah.
Okay.
Is the
Wait,
lecture,
what?
do you know if the lecture is going to be the same as the colloquium?
The same as? No, of course not. No. Wait, I'm not being, I didn't mean to be just here. I imagine that the public talk will have 0 equations and very small words and lots of pictures, movie sound effect, and the colloquium will have 2 equations, slightly longer words. Okay, let's see. Because there's so much discussion involving the little group in Chapter 9, I thought I would say a few more words about it. The discussion is the best discussion is in Weinberg Chapter 2 and, or Volume 1. And it's, well, let me just go on and say what we have here. A particle of momentum p and helicity sigma is defined as some normalization factor, which you can essentially blow away. This is the square root of x of the energy, and 1 over the square root of the energy. It's a unitary transformation, a Lorentz transformation, acting on a standard momentum and helicity. Notice the helicity is the same. This is just a definition. This is the way Weinberg sets it up. It's the way Wigner set it up a long time ago. And so this is a fiducial, I can't really spell fiducial, this is just my guess as to what it might look like. This is a standard Lorentz transformation. And the reason I say that is that there are many Lorentz transformations that will take some particular vector into some other particular vector. For example, you can, if you start with a vector that looks like this, you can first do a z, I'm thinking this is the zero, this is the z-axis, you know, state law requires a z-axis to point up. So you could first do a z rotation, that wouldn't affect this at all. Then you do your Lorentz boost or something like that, and then you could do a rotation about that momentum. And so there are 2 free rotation variables, may even be others. So in other words, you have to pick your fiducial vector and pick your standard Lorentz transformation. Now, there's an obvious choice of a fiducial vector if m is greater than 0. You just set k equal to the 0 vector with m in position 0, or here I put a position 4, effectively m0 if you want to write 0 at the top, which is probably more sensible. If m is equal to 0, then obviously you can't do that because all the states are moving at the speed of light and have p squared equal to 0, or k squared equal to 0. So now you take k equal to something. Well, in this notation, you'd say 0, 0, 1, 1, for example. Or you could, 2, 2, 3, 3, whatever. In this notation, it would be 1, 0, 0, 1. Okay. So what we have then is L of P, mu nu, k nu is P mu. So this is summed over nu, of course. Okay. All right, now let's see what happens if we make a Lorentz transformation on this state. Capital lambda is the Lorentz transformation. By the way, these U means unitary. It's a unitary representation of the Lorentz group. Lorentz group is non-compact. It's infinite dimensional because there are infinitely many p states. That's why it's infinite. Now, let's act on this with, say, let me try PA, even though I'm copying this from Weinberg, and he loves Greek letters. This would then be U of lambda, U inverse of lambda, PA, U of lambda, P sigma. But now this just takes PA into a linear combination of momenta. Let me skip a line to get to something that looks a little bit nicer. Lambda AB, PB, well, let me skip too many lines there. Wait a second. Now I'm got things a little bit. Oh, that's right. This, yeah, I shouldn't have skipped any lines. This thing is U of lambda. This thing is lambda AB, PB right up against P sigma. PB on P sigma is little pb. So this is U lambda AB, PB like that. In other words, this is the momentum operator. This is an eigenstate of that momentum operator with an eigenvalue little pb. And so what does that tell you? That tells you that PA on that is lambda AB little pb U of lambda P sigma. So that tells you that this state is an eigenstate of P with eigenvalue exactly what you'd expect, Lorentz transformed momentum. Okay. So what that means then is that U of lambda on P sigma is some sum on sigma prime of A sigma prime sigma P sigma prime. In other words, we haven't determined what the helicity, you see the helicity doesn't change here in this original definition, but when you act with the Lorentz transformation, well, what we're sure is that the momentum is nice and simple, it's just the Lorentz transform momentum, but there could be a scramble on the helicity states. But for sure, this P, of course I wrote it wrong, this P is lambda P. It's this old thing. When my left arm is down, you really got to be careful as to what I have written. The notes are perfectly correct. All right. All right. So what do we know here? We know that U of lambda takes P sigma into a linear combination of lambda P sigma prime with some coefficients there. Now let's rewrite this thing a little bit. It's equal to some, again, n of P, and the n of P is not important. But then it's U of lambda, and of course this thing is that, isn't it? So this is U, whoops, sorry, L of P, K sigma. Okay? I think I'm going to switch to Crayola chart. See if I get better images. All right, now we can rewrite this as n of P. Now we're going to do something that's counterintuitive. L, the standard Lorentz transformation corresponding to momentum lambda P. And then we multiply by U inverse of L of lambda P. So I haven't done anything, I've just stuck 1 in here. And then, so I've just stuck 1 right here. And then I'm going to multiply these two together, and I'm going to get U of lambda L of P, and then K sigma. All right, and now I'm going to say, well, this is n of P. Again, that's sort of irrelevant there. U of L of lambda P, that's this term. And then I'm going to multiply these two together, and what we've got is U of L inverse of lambda P, because U inverse of L is U of L inverse. L of lambda P. No, lambda L of lambda P. Yes. Lambda L of P. Let's just put them all together. K sigma. All right. Now, here's the important thing. This thing here takes K, the first one takes K into P. Then this takes it into lambda P. And then this is the inverse of the Lorentz transformation that takes you from K to lambda P. So this one takes you from lambda P back to K. So this whole thing takes us back to K. So it, in other words, L inverse of lambda P, lambda L of P, K is K. Okay. So this is a subgroup of the Lorentz group. And in particular, it's what's called the little group. So this is the little group. And this is one of the cases where the jargon or the technical term actually is appropriate. Whereas in so many other technical cases, the standard term is just, the jargon term is not at all sensible. Okay, so in other words, this thing here, in other words, U of L inverse lambda P, lambda L of P, acting on K sigma, well, this just has to be some linear combination of states It's just a linear combination of states that are have the fiducial momentum and but perhaps some other velocity. Now, in the massive case, this thing is pretty simple. Actually, let me maybe, let's see, do I want? All right, let me just write down one more equation here. U of lambda then on P sigma is some n of P, U of L of lambda P, some sum of A sigma prime sigma, A sigma double prime sigma prime, K sigma double prime, which is just another way of saying it's a linear combination of these fiducial vectors there. And so it turns out to be n of P over n of lambda P. And the sum over sigma prime and sigma double prime, lambda P, sigma double prime. Anyway, so it's a linear combination of these things. And these coefficients actually form, you can see that this is forming, these things are forming a group essentially, because this is really A sigma double prime, sigma prime, summed over sigma prime. So in other words, if I wrote it this way, it would have been, it would have looked, see, this is group multiplication. Now, these things that take K into K are called W. So W on K is K. These are the members of the little group, and they're written W in honor of Wigner. And so in particular, you have Wigner, W mu nu, K nu is just K mu. Now for and also we can say that U of W on K sigma, well, this has to be a linear combination of sigma prime, some d sigma prime sigma of W, K of sigma prime. And this turns out to be a representation then of the little group. W is in the little group. And all right, the final, the bottom line here is U of lambda on P sigma is n of p over n of lambda p, sum on sigma prime, d sigma prime sigma of w of lambda and p. This w is that thing there. U of L of lambda p, k sigma prime. This is p, and w is w of lambda and p is L inverse of lambda p lambda L of p. Okay. So W is a member of the little group. Now, what's the little group in the massive case? Well, the little group in the massive case is very simple. It's things that leave this invariant. So, what are they? What leaves M's? What Lorentz transformation leaves 0 M invariant?
Rotations.
Don't all shout at once. I have trouble distinguishing the voices. Lorentz transformations are rotations and boosts, right? Does this stay invariant under a boost? No. What about a rotation? So these are, in the little group is the rotation group for m greater than 0. So for m greater than 0, this d of w is a rotation, and d, let us say sigma prime sigma, this is the 2j plus 1 squared, 2j plus 1 by 2j plus 1 representation of the rotation group. These matrices then are square, 2j plus 1 by 2j plus 1, and they're unitary, in fact, and finite dimensional, and the rotation group, of course, is compact. On the other hand, when m is 0, the rotation group, not the rotation group, the little group is kind of funny. Its actual mathematical name is ISO2. So it's the isometries of the plane. And what things leave distances invariant in a plane? Well, translations and rotations in 2 dimensions. So what we have then are translations and rotations in 2 dimensions. So this is for then m equals 0. And now W then, it turns out you can write it as a translation times a rotation. And this is a Lorentz transformation, but it looks like a rotation on 2 of the 4 coordinates. Looks like a translation on 2 of the 4 coordinates. Anyway, this formula becomes simpler, actually, in a sense simpler, in a sense more mysterious. U of lambda on p sigma in the m equals 0 case is the square root of lambda p. These n's are basically 1 over the square root of the energy. It's e to the I sigma theta of lambda and p, lambda p sigma. So here it's simple because the helicity doesn't change. So if it's right-handed, it stays right-handed. Sigma, of course, is the helicity. So this is just plus or minus. It's e to the plus or minus I times theta. So it's a phase. Okay, I think, yeah, well, anyway, Weinberg goes on to show, and Schwartz is following Weinberg, basically, that u of lambda, a mu of x, the inverse of lambda, well, this is lambda inverse mu nu, a nu of lambda x. Now that's what we would have thought if we didn't know anything about little groups and hadn't read Weinberg, but in fact, there's an extra term, which is the gradient of some scalar. And that means that under Lorentz transformations, the polarization vectors change this way. They become e mu lambda p plus or minus 1 times a phase, e to the plus or minus I theta. But then there's a term minus p mu times some omega plus or minus. So in other words, under a Lorentz transformation, you don't just Lorentz you multiply the polarizations by a phase, and then you add or subtract a momentum. Something proportional to a momentum. Okay. So that's sort of background, and now maybe there's a question. All right. The Ward identity. Remember, the photon propagator in general is minus I over p squared plus I epsilon. That's the part that's simple. Well, eta mu nu. And then there's this gauge-dependent part, 1 minus c p nu over p squared. So now I want to go look at E plus E minus goes to 2 gammas, and see that see what happens if we displace a polarization vector by a momentum. Or in particular, we want to see that this term drops out, actually, which will be show us gauge invariance. Okay, so there's the T channel amplitude, and this time, instead of actually integrating over space twice, I'm just going to use the Feynman diagrams. And, okay, so this is P2, but P2 is actually going this way. This is a positron coming in, electron P1, P3, and we've got a polarization E3 mu, P4, epsilon 4, mu or nu if you want. All right. And this momentum is P1 minus P3. Okay. So what is this? First of all, minus IE P1 plus P1 minus P3. This comes from 917. In 917, it's IE, and then everything here is a minus sign. So it's minus this momentum and minus that momentum. So I pulled out the minus. Then we have this vertex. Now what we have is P1 minus P3 coming in, and what we get is IE P2, that's the, well, P2 with a minus. Actually, I forget what the Feynman recipe is, so let me just give you the correct answer. Minus P1 plus P3. So we've got Yeah, the diagram was this way, and so I have to flip that and this. No, the P2 is the way it is, I have to, that's right. So the diagram 9.18 has, it looks like this. And so this is P2, and this would be P3 minus P1. Okay. Anyway, and then what we have is the propagator, which is I over P1 minus P3 squared minus M squared, and then we're going to contract these with the photons, E3 mu star, E4 mu star. And remember, of course, P1 plus P2 equals P3 plus P4 because four momentum is conserved. And so in particular, this means that P1 minus P3 is P4 minus P2. And so now this IMT is, I'm going to pull a minus sign out of there, and I'm going to get minus IE squared, and then that I is there. And then this one is 2P1 minus P3, and this is dotted in a Lorentz sense into these polarization vectors. So this is really a mu and a nu. I should have mentioned that. So, in fact, we can just write this more conveniently as epsilon star there, and this is just dotted into that. And then this one, if I, P3 minus P1 is P2 minus P4. And so this one, if I pull out the minus sign, is P4 minus 2P2, and this is dotted into E4 star. So those are the, that's the 4 algebra. And now let's multiply this out. P1 is an electron, or a selectron, on the mass shell. This is an external electron, so it's on shell, so P squared is M squared. So this P1 squared cancels the M squared. And then what we have left is minus 2P1 dot P3 and P3 squared. Now, we could set P3 squared equal to 0, because the photon's also on shell, but we're not going to do that. We're going to do we're going to not use that because we want our relation to be a little more general. So what we get down here then is P3 squared minus 2P1 P3. Okay. We all happy? Actually, I see I've now screwed up. Well, let me factor out an I, and we get MT is equal to E squared P3 E3 star minus 2 P1 E3 star P4 E4 star minus 2 P2 E4 star. And all that's divided by P3 squared minus 2 P3 P1. All right, so that's MT. Now, IMU is the related diagram, but with P3 epsilon 3 mu star going off this way. And now, this one emits P4 epsilon 4 star. And so this is P1 minus P4 is the momentum on this one. And now if you put all that together, you get minus IE 2P1 minus P4 on epsilon 4 star. And IE, I over P1 minus P4 squared minus M squared, and the IE multiplies P2 plus P4 minus P1, and that's contracted with P3 star. Okay, so that's what the Schwartz-Feynman rules give us, and once again, we have P1 squared cancels M squared, and so we have then minus, well, we can do that, but since we want to combine that with this, we see that P1 minus P4 squared is the same thing as what we had here, and let me write it in exactly the same way. It was P1 minus P3 squared. Oh, wait a minute, that's not right. It's it's P2 minus P3 squared. And so it's P2 minus P3 squared. And so, let me just skip a few steps here, and we get IE squared P3 epsilon 3 star minus 2 P2 epsilon 3 star P4 epsilon 4 star minus 2 P1 epsilon 4 star. And all this is divided by P3 squared minus 2 P3 P2. So the point is that we can swap P1 minus P4 for P2 minus P3, and then the P2 cancels the M squared and we get this. Okay. Now, there's a third diagram, and let me write that one down quickly. This IM4, this is the one that looks like this. And here it doesn't matter whether we call this 3 or 4. This whole thing is 2I E squared A to mu nu epsilon 3 mu star epsilon 4 mu star, which, now that I think about it, is just 2I E squared epsilon 3 star epsilon 4 star. In other words, it's the Lorentz contraction of those two. And this comes from equation 9.23. So now here's the cool thing. Suppose we replace one of these epsilons, say epsilon 3 star with P3. And that's the sort of thing that happens when you make one of these Lorentz transformations. That is to say, this epsilon of P turns into the epsilon of P, and then there's a minus P or a plus P, depending on what omega is. In other words, the epsilon gets shifted by a P, and the P is that P. Okay, so what we're going to do then is, to make things simple, just set epsilon 3 star mu equal to P3 mu. And then we add up these diagrams, these amplitudes, mu plus mt plus m4. And what we get is E squared over P3 squared minus 2P3 P1. And then this is, it starts out looking as something of a mess, namely P3 squared minus 2P1 P3, but then we notice that's the same as the denominator. And this part is P4 epsilon 4 star minus 2P2 epsilon 4 star. And the next term is P3 squared minus 2P2 P3. And what do you know? That's also the same as, well, no, it's not. Let me make sure I keep everything straight here. What I'm a little puzzled about is this. I've got in the denominator of mu, I've got a P1 here, and I want to cancel. I want to say that this one has a P1. Well, just following my notes, where I think there's actually a mistake. This is epsilon 4 star minus 2P1 epsilon 4 star. And then all that, and then 2E squared P3 mu epsilon star 4 mu. That's what happened when you contract with this, but you replace this with the P. So we never use this term here. Let me look. Do you see what those?
You have a different denominator.
All right.
They're different propagators for both of them, so. Yeah, but P2 is the cancel.
Let me just see. Okay, does somebody see a mistake here? Anyway, I'm going back to look here at mu. No, mu we've got. Oh yes, mu. So mt was the one that seemed to be fine. Then there's mu. This looks like. Okay, mu. That's exactly what Schwartz has.
But isn't that okay though?
Yeah.
I mean, you got P1, P3, and P2.
Oh, you're right, you're absolutely right, thank you. You get two, all right, yeah. I need an eraser here, so let me. Get this eraser. All right, first I have to. I played baseball in college.
Yeah, I'm on the go.
All right, so as David is pointing out, this one is divided by P3 squared minus 2P3 P1, and this one is divided by P3 squared minus 2P3 P2, and that one isn't divided by anything. So this cancels this, that cancels that, and what we wind up with then is factoring out a 2. You get 2e squared times P3 plus P4 minus P1 minus P2, E4 star nu. And of course, by momentum conservation, this is 0. So the 2P4 comes from these two terms, and the minus P1 and minus P2, the 2's come from those. And where the hell did the 3 come from?
The last one.
The last one. Ah, the last one, thank you. Okay, you get 2 also. Future baseball player. Okay, any questions? All right, so this tells us that, in particular, one of the things this tells us is that the awkward term from well, this tells us that the gauge transformation associated with the Lorentz transformation doesn't do any harm. In other words, we've got basically that m, in other words, if we had m mu nu epsilon, say 3 mu epsilon 4 nu star, and we replace one of the epsilons by a p, the thing is 0. And that's one version of the Ward identity. Now the fact that we didn't use the fact that these momenta, these photon momenta had satisfied p squared equals 0, or q squared equals p squared, let us say equals 0. And so we can think about a more complicated diagram that looks like this. Some q here, some k there, and this one is then P1 minus Q, P2 going that way, and those ones there, and in here is some sort of a mystery that we're not going to examine too carefully. And if we looked at this, then we would have, for example, we'd have that mt was an integral d4 q, d4 k, 2 pi to the 8th. These are the loop momenta that we'd be integrating over. And then there'd be a momentum and energy conserving delta function. And then the analog of what we just did would be E squared Q mu minus 2 P1 mu K nu minus 2 P2 nu, and then there'd be these photon propagators here and here. And these would be these ones with the C in them. And then it would, that would be contracted with some X alpha beta of Q and K. All right, and I left something out. Namely, this thing here would be Q squared minus 2 Q dot P1. So this part is essentially analogous to what we did, but then instead of the final state photons, we've got these loop diagrams. And now we have to add in the other diagrams, namely there'll be a diagram like this. there'll be the U diagram, which is written this way. And then finally, there's the simple diagram due to the fourth order vertex. Those are the photons, and these are the electrons. Now, if you add in all of them, what you get is you get mt plus mu plus m4 equals e squared integral d4th q d4th p 2 pi to the 8th delta function p1 plus p2 minus k minus q. And now q nu minus 2 p1 nu k nu minus 2 p2 nu. So this is the T diagram. Okay. Oh, and then there's more. Pi, x, alpha, beta, mu, alpha, nu, beta. All right. Oh, this is more complicated than my life. All right, we're almost done. Now, what we want to check is that the pi, within pi, the part of pi, where did I write pi down?
There?
Yeah, all right. So what we want to see is that this part, the 1 minus c part, goes away. And so in other words, we're going to replace pi, we'll just do one of them. Pi mu alpha we'll set equal to some c times q mu q alpha. All right, what's the change in that if we make that change? Well, the change is delta, just delta m, let me say. The big C, e squared, integral, again, d4th q, d4th k, pi to the 8th, big delta function. And now, what's left in that we're setting this thing equal to a, there's going to be a q mu here and a q alpha, and the q mu gives us, well, q squared minus 2 p1q. So that term cancels. And what we get there is k nu minus 2 p nu 2. And then there's a q alpha that all right, maybe I'll write the q alpha here. So that's the first term, and now the q mu into the second term, well, this is q squared minus 2 p2 dot q. So that's that. That one cancels. And we get plus k nu minus 2 p1 nu. And then finally, q mu on this just turns into 2q nu. And so this is plus 2q nu, although this eta is really other. Okay, it's all that, again, times pi nu beta x alpha beta. And now, this is in fact 0, because what this is, if we factor out a 2, we get k nu minus p2 nu minus p1 nu plus q nu. And this is the thing that's 0 because of the energy momentum conservative delta T. And so the whole thing is 0. And so we're verifying then Ward's identity, that if you shift an epsilon by p, as you must in when you make a Lorentz, to respect the gauge transformation that's associated with the Lorentz transformation, you don't get any change. All right. Now, there's one more thing that I'd like to sneak in today, but before I do that, let me see, did I bring my notes on this, or did I not? Hell, I forgot those notes. All right, so I'll just go on with what I plan to do. The thing that I left out that I was going to talk about, just as a tidbit, was how you actually use the Mandelstam variables the way I did at the very end of the last lecture. And it's simple algebra, but you know, you've got 4 different four momenta, and if you go in the wrong direction, you don't get anywhere, you go into the weeds. And but I didn't bring my notes, so let me so let me just say, if you want, I'll do that at the beginning of the next lecture. All right, the topic now is something that's quite interesting. This is again a Weinberg result. So this is Stephen Weinberg, PhysRev B 135. B was the particle physics part back in '64, and it's page 1049 to 56. And this is really quite cute. The idea is that Lorentz invariance implies charge conservation, and so let's see how this works. First of all, imagine we have some amplitude which we can write diagrammatically as pi comes in some blah. Okay. Now, suppose we add an external photon on this line. Well, then this goes into mi of pi and q, which is the diagram. I seem to have lost an I there, but anyway. Pi comes in, a q goes out. Oh, that's a straight line. So, and the lines are, my straight lines are dotted in Schwartz, but I have trouble writing dotted lines. And this line here is pi minus q. So now what is this mi of pi and q? Well, this is this selectron vertex, and this would be then minus IE. This selectron propagator, I over pi minus q squared minus m squared. And then this vertex, which one might have written first, but anyway, that vertex is pi mu plus pi mu minus q mu epsilon mu, and then whatever this thing was, which is m0. And it's m0 of pi minus q. All right. Well, first of all, this q is an on-shell photon, so q epsilon is 0. pi is an on-shell electron, so pi squared is m squared. So this thing is actually minus E, and the minus, I'm pulling this minus, I don't know where I'm pulling the minus sign from, so let me just leave it as, this is, oh, it comes from the denominator, because in the denominator we're going to have minus pi dot q. But q squared is 0. We're going to use that. So this is minus 2 pi q. So let me write this. Plus minus 2 pi q. Up here, it's just 2 pi epsilon. Because q is 0. And then this is m0 of pi minus q. Okay. So we make a plus there and put a minus sign there. We cancel the 2's. And now what we do is we take what's called the soft limit. This means we're looking at this in the limit of small q. Well, in the limit of small q, we can neglect this q here, and we just have what's left. All right. Notice, however, that most of this denominator went away. Why? Because the photon was attached to an external electron line. That meant that we had p squared equal to m squared, so the big terms went away. And the photon was also external, so q squared was 0. If we were to attach this photon to one of the internal lines, like this, or, well, we can't attach a photon to a photon line, but we attach a photon to some internal electron line, we wouldn't have p squared equals m squared. The thing wouldn't cancel. And so instead of getting something big, which is 1 over something small, q, we'd have something that was integrated over and was typically big. All right. So the dominant thing then is the addition of this q to the external lines, not the internal lines. And now we have to repeat the same thing for 4 different cases. The different cases are whether there might be an incoming selectron, typical ape behavior, apes throw things. Actually, elephants throw things too. So I went to the zoo, and I think somewhere in Paris probably, and there was some elephant that was annoyed at the public. I don't know, maybe somebody was smoking and the elephant didn't like the smoke, or maybe the elephant was asking for treats and didn't like the treats that the people were tossing to it, and so he's picking up things and throwing at the people who were standing there looking, the visitors to the zoo. All right, so suppose we have an incoming positron. So then we would have mi of pi and q, and in the soft limit, this thing would be, oh, I forgot to do the soft limit of the electron. So the incoming electron is minus e pi dot epsilon over pi q m0 of pi. And we can leave out the q there because q is so small. If it's an incoming selectron, then it's the same thing in the soft limit, but this minus e turns into plus e because the charge is positive. So this is e pi epsilon pi q and 0 of pi. Whatever the p happens to be. An outgoing selectron, so this looks like this. This goes to, I'm writing this backwards instead. So this is pi plus q pi. Outgoing selectron the amplitude here is, well, it starts out as mi, or pi in q, minus IE, I over pi plus q squared minus m squared. So this is very much a repetition of what we've just seen. And here, pi plus q, epsilon m0, pi plus q. You take the soft limit, and this one is e pi epsilon piq m0 pi. And now if it's an outgoing positron, it's mi of pi and q is just minus e pi epsilon piq and 0 pi. Okay. Now we sum up all the amplitudes for the emission of a photon by this diagram that has a number of external positrons or selectrons. And if we add them all together, what do we get? We get m is equal to E it's E m0 and it's m0, I guess, of all of these pi's. It's the way to think of it. And now we would have some on the incoming and charge, whatever the charge happens to be. Schwartz writes it as a big Q for some reason. Anyway, pi epsilon over piq minus the sum of outgoing qi pi epsilon piq. Okay, now under, and these are different, I incoming, I outgoing, say. All right, now we're going to do a shift, do a Lorentz transformation, and then there'll be an associated gauge transformation, and that gauge transformation will displace each of these epsilons by something proportional to k, or actually to q, where q is the momentum of the photon. So there'll be an extra q. Well, what happens is this thing cancels and just becomes 1, and so the change, the violation of Lorentz invariance is delta m, and that's E m0, and this just becomes 1, right? So it's the sum qi incoming minus sum qj, say, outgoing. But if you want the violation of Lorentz invariance to be 0, then you need conservation of charge. So Lorentz invariance implies conservation of charge. And that's one of these striking things. The way Weinberg was thinking about it in his 64 paper was something like, if you couple charge to a massless spin 1 particle, then the charge has to be conserved. If you want Lorentz invariance, of course you want Lorentz invariance. Okay. So, are there any questions? All right. Let's see if we can generalize this just a little bit. Here we were talking about, we were using a particular form of the interaction, namely the form of scalar electrodynamics. Suppose we had something more general. So this lecture today was, and I mean, I'm following Schwartz and Weinberg, and so this is just very conceptual. All right, so let's think about this. So let's first of all imagine we have a general interaction. Schwartz writes a triangle. Actually, let's just call this P plus Q. And now we have Q coming in. So this is the picture. And we're going to represent, we're going to say this is minus IE. You can always do that. And then we're going to say this is some gamma mu of P and Q. Well, that's certainly fair. But now, this gamma mu is going to be some vector, 4 vector that depends upon P and Q. And it turns out that this gamma mu, let's write it up now, 2p mu times some f, and since it's a function of p and q, it can only be a function of p squared, q squared, and q dot p, because it has to be a function of things that are Lorentz invariant. And then the other one is q mu, g of p squared, q squared, pq. Okay, these things are called form factors. So they change a vertex that is just something very simple, namely in the scalar electrodynamic case, it's actually not quite so simple. Because it has this term, these momenta that come from a derivative. In QED, it'd just be a number, like minus IE. And in fact, well, we factored out the P and the Q, so in scalar QED, F and G are just 1. All right, now, we're also going to go to the soft limit. Well, what do we have? We have P and Q are both on the mass shell. So consequently, P squared is M squared, Q squared is 0. And so this thing is really just a function of P dot Q over M squared, say, because it has to be a function of something that's dimensionless. And so this is going to be 2P mu F of Q dot P over M squared. We'll sort of change what we mean here in a sense. On the other hand, this term we can blow away because Q dot epsilon is 0, and so we can forget this term altogether. And so now we're going to modify this by adding an external leg. Just some diagram, but this is the way we add the external leg. In other words, it's more complicated than previously. So in other words, we're going to have something like this. In comes a charged particle, out goes a photon Q, and then Pi minus Q goes into some blob. So this is what we're going to be talking about. And now we would say that this would be minus E, some Fi of 0, 0 is the soft limit, Pi dot epsilon over Pi Q, and then some M0 Pi. So in other words, what we wind up with is the same thing as what we had over here. It's just that the M0 is multiplied by a gamma of 0. Not a gamma, an F of 0. And so the same result holds, namely, if we displace epsilon by Q, and notice there, if the epsilon were changing by Q, we would have, well, we'd either have Q squared, which is 0, or we would have Q dot epsilon, which is 0. Anyway, summing up all these diagrams, what we would have would be, instead of this, we'd have this multiplied by an F of 0. And so once again, we have the rule that if you want to have Lorentz invariance, when the epsilons change by Q, then you've got to have the sum of the incoming charges equals the sum of the outgoing charges. And so once again, in this more general sense, Lorentz invariance implies charge conservation. Okay, are there any questions?